As you can tell,
Yeah.
I adore doing the Laplace transform integrals. They're just such fun. I don't want to do these damn integrals. So if I want to avoid doing the integrals, I need to figure out ways to adjust functions we already have and incorporate that into the Laplace transforms so I can use this formula sheet I did. I'd like to figure out how to rearrange pieces, things that show up in my differential equations frequently. So, for example, we saw things like this, right? And if I'm going to try and do the Laplace transform of this function, that's going to be taking the integral from 0 to infinity of this. We talked about this. What do I have to do that integral? Right, but more than that, because this particular integral and that's, why is that even more disgusting than just having to put a limit in it, yeah? It's parts twice and then I have to, no, bleh. But it turns out that e to the 2t piece can be combined with the e to the s piece. Hang on a second. I could rewrite this as the integral from 0 to infinity of e to the what times sine of 3t. Yes, but I'm going to adjust that just a little. I'm going to write it as minus s minus 2t. Because then it still looks like e to the minus st, e to the minus s minus 2t. That's a u sub away from being the regular Laplace transform, isn't it? The only difference between this and the regular Laplace transform is instead of s, I have s minus 2. So I could do a u substitution here. If I did u is s minus 2, I'm integrating with respect to t. I don't ever use u as du in this at all. I'd get a Laplace transform, only instead of having a function of s, I'd have a function of u. Swap back, and you're going to get wherever you had an s in the Laplace transform, you're going to place it with an s minus 2. What is the Laplace transform of sine of 3t? Grab the formula sheet. Right. Sine of at is a over s squared plus a squared. But if I did the u substitution up here, where I wrote u equals s minus 2, then down here, I'd have 3 over u squared plus 3 squared, wouldn't I? So coming from here, I should get because that's the Laplace transform with a change of variable up there. Is there anything particularly magically special about the 2 I used in this entire process? The only reason I used 2 the only reason I used the 2 was because it was the 2 up here. This works every time. Every time I have a factor of e to the something t, I can do this sort of substitution, and it's just going to adjust the Laplace transform by a shift. If I multiply by e to the at, my Laplace transform is shifted by a. It's shifted to the right. Because our functions are of exponential order, big O of e to the t, what I've got here is every time I bring in another factor of e to the t, I'm not actually multiplying, I'm adding like I add exponents. And that picks up my graph and moves it over. The change in the S domain is a translation. Now, before we freak out, the very first 2 formulas on the formula sheet. What's the Laplace transform of 1? So the Laplace transform of e to the at is the same as the Laplace transform e to the at times 1 is going to take this and replace this s with s minus a. And as a matter of fact, that's formula number 2 on the sheet. But that means when I see e to the t and sine t and e to the t and cosine t and all of these other things where I've multiplied by e to the t, I don't have to redo the integral definition. I want you to imagine for a second that I asked for the Laplace transform of t cubed e to the minus 2t. If I wanted to do this by the integral definition, we would have to do integration by parts 3 times. I'd rather hit myself in the head with the textbook until I was unconscious. That's bullshit. But because I can think of this as my a multiplication up here, I just have to think about what I would do to t cubed. So really, I'm going to take the Laplace transform for t cubed, and I'm going to shift my s value. I need to write down somewhere on here that I want to shift s. The way I'm going to write that down is I'm going to say that s is going to be shifted to s minus -2. So I grab my formula sheet. What is the Laplace transform of t cubed?
You need the piece of paper. 3 factorial over S4.
3 factorial over s to the fourth. Wait a minute. I still need to do the shift, don't I? Right? I haven't done the shift there. So let's do the shift, and I get 3 factorial over the quantity s plus 2 to the fourth. There's my shifted behavior. Now, it even says in the textbook that this is only valid for s bigger than what? But on our formula sheet, it gives me a c. Exactly. Right there. Which means this is only good for s bigger than -2. Now, the reason that limitation comes up in the s is because when we did the integral from 0 to infinity. And so we're really pinning our fact on the idea that e to the 0 is a known quantity. Try this one. You will notice that I keep forgetting to use the fancy squiggly braces for the Laplace transform. It's a pain in the neck to write. I don't care if you use the braces or parentheses. It's not going to bother me. I'm going to have to exploit my linearity here.
What do you mean exploit linearity?
I really don't want to do this as one Laplace transform. I want to do it as 3 separate ones. This is really the Laplace transform of cosine 5t minus the Laplace transform of e to the t cosine 5t plus 3 times the Laplace transform of e to the minus 4t cosine 5t. And each of those is either directly on my formula sheet, as the first one, or a shifted version, as are the second and third ones. So, the Laplace transform of cosine of 5t. Exactly. So it'll be S over S squared plus 25. And again, because this is a cosine, I know that's good for S bigger than 0. Minus. What does that e to the t do? Except it's multiplied by something else, right? So what do I do when the e to the thing is multiplied? I take the Laplace transform for cosine of 5t, but I shift it. In this case, by e to the 1t. So I'm going to do s to s minus 1. This is going to be s over s squared plus 25, but it's going to get shifted. What's the last one going to do? Except the shift is different because that's e to the minus 14. It's s minus a, so it's minus the negative 4, making it s plus 4. Everywhere I see an s inside this parenthesis, I replace it with an s minus 1. Everywhere I see an s in this, I replace it with an s plus 4. Questions? So Noah, the multiplication, I can't just multiply the two pieces together, right? Because integrals don't work that way, right? I'd have to do integration by parts. So this is the replacement for that.
Oh, never mind, never mind.
Okay.
Because you said it was shifted. I was about to ask a question, why can't we just plug that into the Laplace transform and number 11?
Right.
And then that's where we got.
That's exactly where we got that.
Yeah.
Yes. So that's what's written here and written here. And you'll notice that's exactly what we just did. And that's why, even though I have these sheets, I remember this procedure better. Whenever I see a multiplication by an e to the something, I'm going to do a shift. The other thing I want to be careful of is working backwards, because if I can do it for the forward Laplace transform, I can do it for the inverse transform as well. So let's think about this. I want the inverse transform of 1 over s squared minus 6s plus 10. Now, my first problem is that this does not look like anything on my formula sheet as written. But I can do a little algebra here. This is going to be the drawback. Every time I'm going to say, I can do a little algebra. So I'm going to have to try and make it look like something we were just looking at. And when I look at these two are the ones that give me the closest hint. How do I get from here to something that looks like these? I have to complete the square. All right, wait a second. S squared minus 6S plus 10. Complete the square. So I have to put something inside the parentheses to make that a perfect square. And I have to put the opposite of that on the outside. What number gets added here?
+9.
So if I put a +9 on the inside, I have to put a -9 on the outside. And I get S minus something squared plus 1. What's the something? Bingo. Which makes this the Laplace transform of, sorry, the inverse transform of 1 over S minus 3 squared plus 1. And that looks like Formula 11, doesn't it? Hot damn. It's a shifted version of A over S plus A.
Do we need the S minus?
Well, here I have the S minus, right? That's what the shifted version is from here.
What are you talking about, 10?
Oh, I'm sorry, I said 11. You're right, 10. 10. My apologies, you're right. If I was using 11, I would need the S minus. I don't have an S minus on top. I only have a number on top. You're right, that's Formula 10, not Formula 11. Yep, misspoke, misremembered which one was where. But that means it's a sign, right? And this 1 here means it's sine of t. What's this mean? Exactly. Which again gets me around doing undetermined coefficients with the sine and the cosine and the e both in there. I didn't have to do anything. Unfortunately, this means that I will run into places where I have to do a lot of algebra rather than just a little algebra. I'm telling you right now, this one's atrocious, but it's just algebra. What algebra do I need to do here?
We can break it up.
How?
See what it's all. I guess it doesn't.
Yeah, and that's still going to give me ugly crap on the bottom, right? I could, but that's actually going to make the problem unfortunately worse. Because what am I going to have to do once I get that? I'm going to have to do partial fractions. So I might as well just do the partial fractions from here. The problem is that the partial fractions is something over s squared, something over s plus 1, something over s plus 1 quantity squared, something over s plus 1 quantity cubed. I got to do a 5-way partial fraction. Blah. It works, it just sucks. Oh, okay. Teach you to open your face. Ready? I'm going to cross multiply by all of my common denominators. So I multiply by this on both sides. I get 2s minus 1 equals a s plus 1 cubed, because 1s would cancel. Then I'd get b s plus 1 cubed. I'd get c s squared s plus 1 squared. I'd get d s squared s plus 1, and I'd get e s squared. Everything else is just multiply and gather like terms. A s to the fourth plus 3s cubed plus 3s squared plus s plus b s cubed plus 3s squared plus 3s plus 1 plus c s cubed plus 2s, sorry, wait a minute, s to the fourth, 2s cubed plus s squared, and then d s cubed plus s squared plus es squared. Whew. And now we gather all the like stuff. So what do I have for s to the fourth? For s cubed, I got 3a plus b plus d. Oh, plus 2c, right? S cubed, S cubed. Oh, 3b. I can keep track. No, I'll get it right the first time. 3a plus b plus 2c plus d s cubed. How about s squareds? What's my s squared coefficient?
C, wait, let's go 3A, 3B, C, D, E.
My s coefficient.
A plus 3B.
And then the only thing that's got a constant on it is b. Wait a second. 5 equations, 5 variables. The constant here has to equal the constant there. B equals minus 1. A plus 3b has to be equal to 2. And then for the rest of these, they all have to be equal to 0. Because there's no s to the fourth, no s cubed, and no s squared on the other side. So 3a plus 3b plus c plus d plus e is 0. 3a plus b plus 2c plus d is 0. And a plus c is 0. But this one's already done, right? That was easy. And I can use that to get a. A minus 3 equals 2. So a is 5. Now I have a and b. Wait, I have a, I can get c. What's c? And now I have a and b and c, I can get d. 3 times 5 plus -1 plus 2 times -5 plus D equals 0. And then I can get E. Three times 5, 3 times -1, C, D, E equals 0. 15 minus 12, what's E? -3, -5 is -8. 4 more is -12. 15 minus 12 is 3. When I move it over, it's -3. Okay, wait a minute. I want the inverse Laplace transform of A over S plus B over S squared plus C over S plus 1 plus D over S plus 1 squared plus E over S plus 1 cubed. This is 5 times the inverse Laplace transform of 1 over S. What's the inverse Laplace transform of 1 over S? Good. So that's just a 5. Plus, minus, right? Minus 1 Laplace transform 1 over S squared. It's Laplace transform for 1 over S squared. Because I'm going to do 1 factorial over S to the 1 plus 1, that's just T to the first. Now, minus 5, 1 over S plus 1. Oh, forgot my L. L inverse. Got to write in what the hell I'm doing. 1 over S plus 1. That's an E, right? That's E to the almost. Right. Minus 5 E to the minus T. Now, minus 4 Laplace inverse of 1 over S plus 1 quantity squared. We just did 1 over S squared, right? 1 over S squared gave me T. But now it's shifted, which means it's got an E to the something T on it. So this is minus 4 T E to the minus T. It's been shifted over 1. Shifting by 1 multiplies by the appropriate E. And then I get minus 3 Laplace transform 1 over S plus 1 cubed. Wait a second. S plus 1 cubed. It's a cube on the bottom. What should be on the top? But there isn't a 2 on the top. So what do I do? Exactly. And that should be a T squared. But wait, there's more. Haven't heard that since calc. It's shifted. So there's an E to the minus T there as well. Holy crap. Yes.
What do you mean by it shifted?
So I know how to do 1 over s, right? I know how to do s to a power in the bottom. Nowhere up here do I have s minus a to a power in the bottom, except like this, right? But isn't that,
Oh, okay.
it's shifted here, so it's multiplied by the e here. Yes, sir. Where? Okay. Let me get the statement of the theorem back. Statement of the theorem says that whenever I have an e to the at times something, and I take the Laplace transform, the Laplace transform looks like the same as without the e to the at, but it's shifted horizontally. Remember, when you add or subtract outside the graph, the function, like x squared plus 2, you move it up or down. But if you do x plus 2 all squared, you move it. I'm shifting because it's on the inside. So that shift means that there's an e in the inverse transform. So when I say shifted, I'm thinking of this and this and this as being not just an s, but an s plus 1 or an s minus something. It's moved over. Questions? For the record, that isn't the order in which I did this in my notes. I had A, B, and C, and D, and E reversed in my notes. They were all in different places. But I got the same answer. I just did it in a different set of letters. Examples 1 through 4 in the text, which are not the problems I did, walk through this as well, and they actually solve differential equations like this. Let's consider 1. The function 1. We did the Laplace transform for this using the definition, right? When we did the Laplace transform of this, we did the integral from 0 to infinity, which means I really don't care about what's happening when t is less than 0. I could think of this instead of this at a height of 1. I could think of only this part of it, because I was really doing the integral from 0 to infinity when I did the Laplace transform. But since the Laplace transform only cares about from 0 over, what if the function didn't have a left side? What if we consider the function that is only 1 from 0 on? The piecewise defined function, which our textbook calls script u 0 of t. It's defined as 0 when t is less than 0 and 1 when t is bigger than or equal to 0. I have not seen this called u outside this book. In most of the other books, I've seen this called by the name of the guy who came up with it. This is called the Heaviside function. The U comes from the fact that it is also called the unit step function. It steps up once by a distance of 1 unit. Boop. Where am I going to use something like this? Well, I'm going to use something like this when I turn something on. I have a switch. Remember, we said that electrical circuits behave just like the springs? So I can think of, I've got a circuit and I turn it on. And it goes from being off to being on at time 0. But it doesn't just have to start time 0. I can start at any time I wanted. So let's modify this just a little. Let's define UA of t to be U0 t minus a. What? Oh, we're shifting over. 0 if t is less than a, 1 if t is bigger than or equal to a. So this is my new shift function. Instead of turning on at time 0, it turns on at time a. Every piecewise defined function we have can be thought of as a combination of Heaviside functions multiplied by other things. Let's consider this function. If I asked you to graph this function would look like that. Be part of a parabola, right? Probably be steeper than that. I'm a crappy artist today. But it would be, I'm sorry, there should be a solid dot here. There should be an open dot here. It's nothing, it's nothing, it's nothing, it turns on. You could think of this as taking the regular parabola and multiplying by a function that turned on when we got to 2. This one tight. So it's nothing, it's nothing, it's nothing. Whenever t is less than 2, you've got t squared times 0. And isn't that going to give me a 0? And then as soon as you get past or equal to 2, you switch from 0 to 1. So we switch from nothing to t squared. I can use this to turn a function on or off. Let's say I only wanted to use a graph of cosine. Right here, we're going to define g of t is cosine of t, but only between 0 and 2 pi, and at 0 everywhere else. I can think of this as what I want to do is I want to take the cosine function and multiply by a function that satisfies the property of being 1 between 0 and 2 pi, and 0 elsewhere. So this is a function that looks like this, right? It's off, it's on, it's off. So this is a step to turn on at 0, right? I'm going to turn it on at 0. So I know I'm going to need U0 of t to turn it on. Once I do that, I've got a switch that's going 1, 1, 1, 1, 1, 1, 1, 1 until I hit 2 pi, at which point it should be going 0, 0, 0, 0, 0. So I need to cancel out the one that's turned on, right? So I'm going to subtract 1, but it's not going to turn on until 2 pi. It's off, it's off, it's off, it's on. It stays on, and then I subtract another 1 and it goes back to being 1. As a matter of fact, if I want a part of a function, a section of f of t from t equals a to t equals b, I'm going to do exactly this. I'm going to use f of t times ua of t minus ub of t. So I can turn a function on, and then I can turn it off later. I can also do this even if if it switches between one function and another. So let's think about this. This starts out up here at a height of 2, and then switches down. Now again, you might say, when am I going to use this? Okay. The traffic is flowing from right to left, then the traffic is flowing from left to right. I've got directional capability here. Now the problem is that this function starts off on, and this one turns off at time 2. If I wanted it to turn on, it turns off at time 3. If I wanted it to turn on at time 3, what would I use? To turn on at time 3. I'd use 2u3. So I can do that for this part, right? The negative 2 turns on at time 3, right? So this part, that's minus 2 u3 of t. I like that. But this part starts out on and turns off. That's kind of taking our behavior and doing it backwards, isn't it? Oh, wait a second. If when it's starting, it's at 0, and now I want it to start at 1, and then I want it to go from 1 to 0, isn't that just flipping where the 0 is and where the 1 is? What if I did 1 minus u3 of t? What would that do? Well, before 3, that would be on. After 3, that would be off. But I want that to not have a height of 1. I want that to have a height of 2. Because we're starting out at a height of 2. Please notice that I can simplify this. And I can write this as 2 minus 4 u3 of t. Question?
Is there supposed to be a 2 in front of the 3?
Here?
Oh, no. Those are together.
Right, these are equal. Because that's the first part. That's the second part. This whole thing would be both of them. So f of t equals this. Now, back when I first introduced this, I said UA of t, right? I'm writing U3. But I said UA was the same as the original U, just shifted. So another way to write U3 is to write U of t minus 3. It's shifted. Back in the previous example, where I said we'd turn it on at A and turn it off at B, I can write this as U of t minus A and U of t minus B. Those are shifts. Up here with the 0 and 2 pi, that would be U of t minus U of t minus 2 pi. So I can think of those subscripts as shifting my turn on, turn off point. Why? Because in my Laplace transform, my driving function, my non-homogeneous term, could start at some particular point in time. And we have, again, another theorem. And it says, theorem 7.3.2, if the Laplace transform of f of t is capital F of s for s bigger than c bigger than or equal to 0, and a is bigger than 0, then the Laplace transform of f of t times u a of t, which is the same as the Laplace transform of f of t times u t minus a, is e to the negative as f of s. Please put a big star next to that negative. This is the reverse of the translation idea that we were just dealing with. When I said, hey, I see an e to the at, so I get 1 over s minus a. Well, now I'm saying I want to translate the t part, not the s part. That's what this does. It translates t. Well, then we end up with an e, but it's the other way, so it's negative. We got e to the at, we get e to the negative as. I'm going to use this more often in the inverse version. The inverse version tells me that when I see the inverse transform of e to the negative as f of s, I get f of t u t minus a. So this means I'm going to get places where my Heaviside function shows up. Now, the hard part here. Oh, see, hard part here is I made a copy error. Let's fix something. Stop. I made a copy error right here. Big red circle. I screwed something up. Right here. It's f of t minus a. The same shift has to be in both parts. That's important. And that means that's here also. My apologies. I need to ensure that I have the shift in all the bits. Let me do an example. The Laplace transform of this function. What's the Laplace transform of 2? Minus. What's the Laplace transform of 4? But there's this u to the t minus 3 here, right? So this is 4 is the same regardless of whether I shift it or not. This is going to get multiplied by e to the negative 3s. That's our extra piece right here. Here's another one. And this is why I need that shift comment. Promise, this is an example where it comes back and bites me in the ass. I am perfectly fine with the Laplace transform of t. What's the Laplace transform of t? But in order for me to do this part, the shift is t minus 1, which means the outside function needs to have t minus 1s in it. It doesn't, it only has t's in it, right? Crap. I need this in terms of t minus 1. Again, let's mess with it. T is the same as t minus 1 plus 1, right? We kept talking about multiplying by 1. This time I'm adding 0. Subtract 1 plus 1, it balances out, right? So I'm going to replace this t with this. So I'm going to rewrite f of t. It's t minus t minus 1 plus 1 u of t minus 1. And I'm going to split that up. t minus 1 u of t minus 1 minus another 1 u of t minus 1. Why is that a minus, not a plus? Outside the parentheses that needs to be distributed in. These match now. If they don't matchy match, I can't do this problem. So the Laplace transform of t is 1 over s squared. What do I get here? This is this part right here. T minus 1, u t minus 1. So I should get the same Laplace transform and an extra factor of e to the negative 1s. I get the same Laplace transform and a factor of e to the negative 1s. But wait, one more thing. What about this? Almost. I definitely get the e to the negative s, but what's the Laplace transform of 1? Exactly. Whew. Now we will often see the terms that came from the shifts grouped together. This bothers me. It's not a huge bother, but it's still a bother. There is a method by which we can move that translation into the integral of the Laplace transform. There's an example in the book that does this, shows me another way to do this same problem without actually doing the translation out here. Let's take a look at this idea for a second. The Laplace transform tells me that this doesn't get turned on until A, right? Before A, this is equal to 0. So this is really, instead of being the integral from 0 to infinity, g of t u t minus a e to the minus st dt, this is really starting at A. Oh, not t up here, infinity up here. Ooh, don't mess that up, Joshua. Ooh, bad idea, bad idea. I'm going to do a u sub. I'm going to do u equals t minus a. If I do that, what's du? Well, that's nice. And that means that this integral is now g of t minus a e to the, e to the what? e to the minus s u plus a. Oh, wait a minute. That's a u. du. That's a Laplace transform. But it's the Laplace transform of, oh, wait a second. What happens? This is going now from 0 to infinity. That's a regular Laplace transform, isn't it? It's just been shifted the wrong way. Oh. That's the Laplace transform of g of u plus a. Except for the letter, that's the same idea, isn't it? It's just u instead of t, right? So let's just call it t instead. Now, why the hell does that happen? Well, because I also have this e to the extra a here, right? E to the minus sa. E to the minus sa. Wait a second, that's e to the minus sa f of s. Same Laplace transform, isn't it? So, what I could do with that t minus tu t minus 1 is I could say what I'm going to do is I'm going to do the shift here. I'm going to say we take the Laplace transform of t, and then we do the e to the minus s, and we take the Laplace transform of, shift it over. We shifted the other way, right? Now, before you freak out at me, what's the Laplace transform of t? What's the Laplace transform of t? What's the Laplace transform of 1? And if you look back, that's the same thing we got the other way, didn't it? So we can think of readjusting our shift or doing the algebra to match the inside and outside functions. I don't know which one you're going to think is easier. $64,000 question. Why? Here is a first order differential equation. And I'm going to give you initial conditions also. Y of 0 equals 0. Using any method we have so far, I don't know how to solve this. Because the right-hand side is not continuous. It's not going to work by undetermined coefficients. It's not going to work by variation of parameters because that right-hand side F's me over. Until I realize that that right-hand side is a Heaviside function. It's off, then on. As a matter of fact, this right-hand side goes from off to 5, and it turns on at 1. which means solving this with the Laplace transform is easier than any other method I've got. I need something, though, from yesterday. I need the Laplace transform of a derivative. What's the formula for the Laplace transform of y prime? That's formula 13 on the formula sheet, I think. Yes, 13. Plus another Laplace transform of y equals 5. What's the Laplace transform of 5? Well, it's the Laplace transform of 1. So this will be 5 over s, but there's a shift e to the minus 1 s. What's y of 0? Oh, y of 0 is 0. So this becomes s plus 1 Laplace transform of y equals 5 over s e to the minus s. All I have to do is divide. Laplace transform of y is 5 over s times s plus 1 e to the minus s. I now need to do the inverse Laplace transform. Since I see an e to the minus s, I'm going to get a u1 of t. At some point, I'm going to get something that turns on at 1. But what I need to know is what's the inverse transform of this? 5 over s plus 1. What do I need to do? Which means partial fraction time. I'll cheat. I did this one already. So I have the Laplace transform of y is 5 over s minus 5 over s plus 1 times e to the minus s. Wait a second. 5 over s e to the minus s, 5 over s plus 1 e to the minus s. What's the inverse transform of 5 over s? The e to the minus s, though, means I get ut minus 1. What is the inverse transform of 1 over s plus 1? I took the 5 out front for the moment. Right. E to the minus t. Wait a minute. There's a u of t minus 1 here, right? Since there's a u of t minus 1 here, that t becomes t minus 1 as well. A switch got thrown at time equals 1 and stuff started to change on me. That means the solution to my differential equation turned on at 1. By the way, the grapher in our MacBook will do the Heaviside function. There are 2 different examples in the text, As a matter of fact, there are 10 examples in this text section that I really think you should read through. Tomorrow? So you better have done some of this stuff tonight so you can ask me questions about it tomorrow. I will see you all then. By the way, example 11 is about a mechanical engineering problem about a beam. So if you're interested in mechanical engineering, you should take a look at example 11.